Okay, so the final speaker of this mini symposium will be Sankar Das Sarma. So he will tell us and then clarify to us what Wigner, Mott, and correlated insulators and all that means. So Sankar, I'm looking forward to your talk.
Okay, Eugene Demler twisted my arms first to give a talk, and then he told me that probably I should give a perspective. So at first I was very happy that I took his request for a perspective to mean that he thinks I know a lot about the subject, but then I quickly realized that's not true. He thinks I'm old, and so I should know a lot about the subject. So, but I will try to give a perspective, but I will also talk about some recent work done in collaboration with two very strong students at Maryland, Haining Pan and Inwi Vu, and also Feng Cheng Wu, a very good postdoc who just left Maryland, went to USTC as a professor. He was a collaborator in this work with Haining. So I'm going to give you a perspective, some history, and then talk about some recent work. So I'll be covering close to 100 years in 40 minutes, okay? But you have to bear with me. So the basic physics that we'll be talking about here is conceptually simple, but it's quantitatively very difficult to pin down. It doesn't matter what calculations, approximations you use. Either good analytical approximations are valid in an experimentally impractical or rather irrelevant regime, or it's fully numerical, then it's somewhat out of control and you don't really know. So quantitative details will remain difficult to pin down. Basic physics is, and many people alluded to that throughout these 2 days, is that if you increase the ratio of interaction divided by kinetic energy, then electrons will tend to crystallize, localize, trying to lower their kinetic energy by avoiding each other. Coulomb interaction costs energy, so they want to stay away from each other. And the best way of doing it is by localizing. Then they are not going to encounter each other at all. That is true both in classical physics and in quantum physics. And that's the Wigner crystal phase. This effect will be strongly enhanced, obviously, if the kinetic energy contribution is small. When does that happen? Well, it happens when the effective mass is large, or the effective velocity is low, or the band is flat or narrow, or quantum mechanically if the electron density is low. Classically, you want the electron density to be high, or in a strong magnetic field. And we have had talks talking about all these aspects, not so much the classical aspect. I should put a caveat here. I will not talk about the strong magnetic field situation at all. It's a bit specialized, and we have had many talks on that. And also, I have not done anything on it recently. So I would not talk about strong magnetic field. Now, we already know that charged particles crystallize. We call them the lattice. Ions in a solid are crystal, but in plasma, ions are delocalized. So we are now talking about the corresponding electron case. The same can obviously happen for electrons at low enough temperatures and flat enough bands, or low enough energy density. That's all one is talking about. Such a state would typically be an insulator because electrons are localized, but it's not necessarily so. In a finite system, if the crystal is not pinned, it could slide, but we are not going to think about situations like that. In most lattices, the crystal will be pinned and it will be insulator. So basic physics is that you have an energy term, which depends on average separation within the electrons. And in a parabolic system, kinetic energy goes as 1 over Rs squared. Potential energy goes as 1 over Rs, and then you have some correction, which have log terms and so on, but these are the leader power law dependence. So when Rs is much, much larger than 1, you want to minimize the potential energy, and so you'll crystallize. So that's a Wigner crystal. For electrons on a lattice, of course, the energetics doesn't depend on Rs. It depends on potential energy U, some kind of Hubbard U. And kinetic energy is given by bandwidth, not Fermi energy. Then you want U over T to be much, much larger than 1. And in either condition, electrons should localize, and we'll call that Wigner crystal or generalized Wigner crystal. So I went back and read Wigner's paper again. It's really the first paper in many-body theory, 1934. And the second paper is Bede's paper on Bede ansatz. And it's kind of amazing that the issue Wigner raised here in 1934 is still equally valid today. And I would not be surprised if 80 years from now, none of us would be here. People are still talking about this physics because the physics of strong interaction and new systems come along and it will arise in some new guise. Now, Wigner actually did not talk about where Wigner crystallization would take place. I read the paper rather carefully. What he said is this: if the electrons had no kinetic energy, they would settle in configurations which correspond to the absolute minimum of the potential energy. These are close-packed lattice configurations with energies very near to that of, and so this is Wigner crystal. He knew that's what is going to happen. And then he estimated energies by assuming that this RS is infinity. What Wigner was trying to do in this paper is not to predict Wigner crystal. That was not his goal at all. To him, it was obvious that if RS is very large, the system will become a crystal. He attached very little significance to it because he was trying to understand sodium. Okay, that was his goal. And what he wanted to do is to have an accurate expression for the potential energy, correlation energy of sodium. And in doing that, he realized that it's not enough to just use low RS perturbative approximation. He needs something large RS also, and he estimated the energy, assuming it to be a lattice, and then kind of interpolated. And I learned something else from this paper, which is interesting. He thanked a person in Budapest who did all the calculations. He just says that all the calculations are done by such and such, who is not a co-author. In those days, Haining Pan and Feng Cheng would not be a co-author with me. I would just thank them in a footnote that they did all the calculations. It's kind of, how the culture has changed. But in any case, to Wigner crystal was an obvious trivial result. He wanted the non-trivial thing. What is the correlation energy for small RS? Then Mott wrote a paper, which is the famous Mott transition paper, a Mott system, 15 years after that. He doesn't cite Wigner. And you read Wigner's paper and read Mott's paper, very honestly, Wigner's paper is like a graduate paper and Mott's paper is like a high school paper. There's no calculation, no equation, nothing, just waving of hands. And it's actually, you read the paper and, in hindsight, you understand why the paper became famous. But if you didn't know anything, you just would not think that this would someday become a famous paper. So what was Mott trying to do? Mott actually was trying to answer a question phrased by two experimentalists, Debord and Verwey, who found that nickel oxide is an insulator. But if you do band counting, nickel oxide is a half-filled band. It should be a very good metal. So there was some conference in 1937 where all these famous people were actively discussing how maybe the whole band theory is incorrect. Because look, nickel oxide is an insulator, a very good insulator. I mean, people are saying maybe, this periodic system, all the tunneling coming through and constructive block interference, all those things do not happen. And again, here also, Rudolf Peierls kind of solved the problem, not Mott. Rudolf Peierls said that, what may be going on is that there is strong interaction between these electrons. And so maybe the strong interaction is not allowing them to take full advantage of this periodic tunneling, and they don't want to move. This was just a point. And this is a note. I found a note, one-page note, where it says, this is very funny. It says Rudolf Peierls comments with notes taken by Neville Mott. So Neville Mott was a note taker of this idea. But Rudolf Peierls, I guess, never thought about writing a paper on this. He did not think this was anything profound. And then Mott wrote a paper 15 years after that. And the problem Mott was trying to solve, he was trying to solve a very specific problem. Wigner solved the problem of what happens if you have a bunch of free electrons in a gallium background, and what is the lowest energy. Mott asked the question, what would happen if you put a hydrogen atom on a periodic lattice, not a lattice, hydrogen would now call it a lattice, a bunch of hydrogen atoms on a periodic system, what would happen? So it's, so the nucleus would form the lattice and the electron. And then he argued that because of interaction, there would be a situation where it would go insulating. Of course, the two ends are the same thing. And amazingly, I found very few papers which look at this problem as the same physics. There's just only one paper by great late Walter Cohn, who wrote a paper, unknown paper. I discovered it because I was very interested in this question. This is the only paper I found. There must be other papers where it already shows up in the title. So when you do a Google search, it shows up. The paper had very little impact, a very nice paper. And Walter basically said that, Mott physics is very simple, but Wigner physics is very, very difficult. So most of his paper is on Mott. And then he basically says, Wigner has pointed out that the ground state of a system of interactive electrons in uniform charge background has a completely different character in the low and high density limit. And then he said, later Mott said that, and I'm going to try to connect the two. And in the end, he said, you know what, the Wigner transition is very difficult. It's a technically very demanding problem. So I'm going to mostly discuss Mott. And he does various things discussing Mott, and he gives some results, how to connect them and so on. And this paper I discovered because I was very interested in this question. And this question has been alluded to a number of times, particularly in the last talk. What is a Wigner crystal on a lattice? Suppose I take a bunch of free electrons and start throwing them on a lattice one by one at a very low density. What would be the correspondence of Wigner crystal there? And this is basically the question Walter kind of tried to answer, but could not quite answer because he was doing completely analytical work. So we have a multitude of confusing and random nomenclature for the same physics. And you can see that from all the questions Philip repeatedly keep on asking. This is all the same physics. It's just a question of how you want to look at it. So, Wigner talked about a lattice for free electrons. Okay, so there is the underlying lattice, nothing to do with the lattice in principle. And he answered the question, they will form a lattice of their own. Underlying ionic lattice is irrelevant here. And the spin arrangement is a non-trivial question, but the spin arrangement in a quantum Wigner crystal is, I would say, still basically an open question. And I think that what David Shepard said yesterday is consistent with what I'm saying. And the reason is basically that the magnetic energy, exchange energy, is exponentially weak in this limit. So it's not so easy to see the details of exactly what the spin configuration is. Mott talked about electrons from a completely different perspective, from a perspective of partially filled band. Here, the lattice is essential, and often you're talking about a half-filled band. Then further complication came when Phil Anderson made Mott-Hubbard very popular in the context of cuprates. So the Mott got changed into Mott-Hubbard, and this is basically talking about Mott state in the context of Hubbard model. Mott's original paper has nothing with Hubbard model. Mott's original paper was electrons interacting with Coulomb interaction, screen Coulomb interaction. Slater, even before Wigner, really talked about what would happen if you include exchange in a band structure theory, and he kind of realized sometime in the 30s that just exchange will lead to an antiferromagnetic state, and if that happens, then the system will dimerize, and you could have basically an insulator. This is a Slater insulator. And we are talking about what is cause, what is an effect. If you believe that antiferromagnetism is the cause, you call it a Slater. If you think antiferromagnetism is the effect, you call it Mott. So it's a matter of taste in some sense. Then there is Bloch insulator, which is when you have a ferromagnet, electron-electron interaction leads to a ferromagnet. And if this ferromagnetic exchange splitting is larger than your Fermi energy, the system will be an insulator. And something like this may be going on in twisted bilayer graphene. Quantum Hall ferromagnet is kind of an ultimate example of such a Bloch ferromagnetic insulator. And then there are Chern insulators, which is when the bands have Chern numbers, one of these things would call them a Chern insulator. And then there is correlated insulator, a term made very popular by Pablo's papers. And now all of the above are correlated insulators. And there could be other interaction-driven gap ground state. They're all the same physics, and depending on the context, and perhaps one's background, use different names. There is an exception, fractional quantum Hall effect. This is the completely flat band system. There is not even any kinetic energy in some sense. But this thing doesn't even crystallize. This thing is an incompressible liquid. So this was a big surprise to all of us. All of us thought it would be some kind of lattice phase, but we now know that this incompressible liquid, which is totally different kind of physics, wins. And I will not talk about that, but it's indeed true that if you make Coulomb interaction very, very strong, and we heard about this today, Wigner crystal set will win here also. And in fact, in higher Landau levels, that's what happens. All these bubble stripe phases in my nomenclature are essentially Wigner crystal type states. So it seems, I looked at the literature very carefully, and it seems that usually Wigner is used for true fractional lattice occupancy of less than 1 electron per lattice site. So if you have 1 electron for every 2 sites or every 3 sites, you call it Wigner instead of Mott. And it's an arbitrary definition, but it's okay. So that will break a discrete translational lattice symmetry. So that's what we say. And you always talk about long-range Coulomb rather than short-range Hubbard when you talk about Wigner. But in real system, you only have long-range Coulomb interaction. Electrons always interact with long-range Coulomb interaction. Hubbard is an effective model. And then you have an incommensurate electron period with the underlying lattice. It could in principle be incommensurate, or it could be commensurate with a discrete symmetry breaking. And if you have an effective Gellium model, like sodium or electrons in gallium arsenide, very low density, then you call it Wigner because you have no basic background lattice there. Okay. So clear.
So Shankar, can I ask a question here?
Yes, please, sure.
But let's say for these filling fractions like 1/4 or 1/3, I would also use a terminology of charge density wave.
Oh, yeah, charge is very good point. I should have put a sentence there, but I'm glad that you asked. In my language, charge density wave and Wigner crystal are essentially the same thing. In my things. It's a question of how many Fourier components you are keeping. Okay.
I see.
A question of how localized you want your state to be.
No, okay. So actually, another question since I started asking. So actually, like in terms of Pfister, I'm curious, like the Slater antiferromagnetic versus Anderson super exchange.
Yes.
Because I thought that this idea of anti-alignment is more like Anderson super exchange, but was it really, are you saying it's already in Slater's work?
This is my belief. And I had a long conversation with Walter Kohn about it, and I could not get to the bottom of it. It turned out that everybody dislikes Slater for some reason. So I could not quite figure out by talking to people whether Slater actually had the idea entirely on his own. That's certainly what Slater thinks. Or whether, maybe somebody else knows, Bart or somebody. I simply, I cannot answer this question. Okay.
Okay, interesting.
Sorry, can I clarify something you just said?
Yeah.
In response to that question. So I had assumed that the distinction between a Wigner crystal and charge density wave is that the charge density wave relies on the presence of an underlying lattice, which you argued the Wigner crystal does not.
Good. So what you are saying, if you look at this slide, my top point, my bottom point, the bottom point will be Wigner, and the top point will be charge density wave. That's fine. But I'm trying to unify all the nomenclature. They're just two-man nomenclature. So Mott is on one extreme, Wigner is on the other extreme, and charge density wave is much closer to Wigner than Mott, but it's on a lattice. I have no problem with that.
Okay, thanks. Yeah.
Then everything you're talking about today is really then charge density wave. Because, even gallium arsenide has a lattice underlying. It's not a Gellium. So Wigner crystal was seen once for sure, but unfortunately, it's a classical Wigner crystal. This is a paper in 1979. It's a very low density electron, only about 8 per square centimeter on the surface of liquid helium. And Mike Grimes at Bell Labs directly saw the shear mode. I'm not going to discuss this paper in detail. It's a beautiful paper. Everybody should read it. Okay, it really is a beautiful paper. And it also teaches you how to write a paper. It's an amazingly good paper. And there's no question that this was a classical Wigner crystal. Even the phase transition occurred at the value of gamma that numerics predicted, 137. Okay. It's a challenge to see Wigner crystal only using transport. I have made this point already, because using transport, you're going to see an insulator. If you have disorder, you're going to see some kind of glass, so it's difficult, okay? Quantum Wigner crystal is fragile because it disappears both with increasing temperature and increasing density, right? So, strong Coulomb interactions require low density. I'm talking about quantum system. So that makes the effective Fermi temperature and any effective gap to be very low. It also makes disorder more important, because low electron density means disorder is more important. So here is a mean field phase diagram that Yuhyun Wang and I created a long time ago for the 2D system. So this mean field phase diagram has your basic Wigner crystal zero temperature phase, this curved line, Here is RS37, which is taken from Sepperly's work. And so this is the T is equal to 0 phase diagram. And then at finite temperature, it melts. And just for your edification, we put in this paper this classical line. So above gamma is classical, and also T is equal to TF line. As you can see, quantum Wigner crystal has a very small region. Classical Wigner crystal is in a smaller region. So when you put this Fermi temperature, you can see kind of that it's a very fragile system. I did not even put disorder here. If you put disorder here, the whole thing will shrink even more. Recently, Inwi Wu did something similar for 1D system, doing an exact diagonalization calculation. Very similar phase diagram we found because it's mean field in 2D and 1D. And all these different lines, which I'm not going to discuss in any great details, depend on how you put your melting of the crystal, what Lindemann criterion to use, what fraction of the lattice constant should you put. But the basic physics is, again, it's very fragile. It will occupy a very small region of your T versus rho space, and that's how you have to work. You have to work in this narrow region or in this narrow region to see it. And if you're unlucky and Lindemann criteria is very stringent, you have to work in this region, okay, which is not going to be easy. So I actually wrote, probably, this is Kongjung Wu's work, but I'm a co-author. I may have written one of the first papers on Wigner crystallization in this kind of honeycomb lattice. Again, this Kongjung Wu's work, which was almost 15 years ago. And in those days, we were very interested in cold atom quantum simulator. Little did we know that this thing will be done much better in TMD systems or in graphene. And the basic idea was that we could construct a Hamiltonian for which we could calculate the ground state exactly, a Wigner crystal ground state. And for fractional filling on over 6, and discrete symmetry is broken. For this particular case, the problem could be solved exactly by construction. And for other fillings, we could do it numerically. But much of the physics that we are discussing qualitatively actually is in this paper, that if the interaction is very strong, you are going to see Wigner crystallization in this honeycomb lattice. And we went ahead and said it should be detected in noise correlation experiments in time of flight, experiments in cold atom optical lattices. Now, of course, this is being done in real solids. So, by the way, graphene does not manifest any Wigner crystallization in continuum because both kinetic and potential energy go linear in square root in density. So they change the same way. So in the continuum, you would not get that. Now, I'm going to discuss now some recent work of Inwi Wu. These are exact diagonalization results, but this will be in 1D system. Now, if you're a theorist, you're immediately very upset because in 1D, there is no long range order. They're very special. Indeed, true. 1D Coulomb systems are special because they have no strict long range crystal in order. But amazingly, they always have very strong short range Wigner crystal order. This falls off very, very slowly. So depending on your taste, depending on your view, depending on whether you're an experimentalist or a theorist like me, who's almost like an experimentalist, you'd say a Wigner crystal exists always in 1D, or it never exists in 1D, okay? So in a finite system, a 1D Coulomb system is always a Wigner crystal. But if you go to a very large system, it's never a Wigner crystal. This is not my work. This is work of late Heinz Schultz in a very important paper, where he showed analytically through bosonization that you have Coulomb interaction, then the density correlator falls off the 4kF, which corresponds to the Wigner correlation, falls off slower than any Paul law. So that basically means that the short range order will persist to arbitrary long distance, although the system has no long range order, okay? And he showed that the 2kF correlation falls off very fast, Paul law, but the 4kF doesn't. And this is exactly what I mean when I say that depending on your taste, you could say 1D Coulomb systems are always Wigner crystal or never Wigner crystal, because if you go to infinite system, there is no order. But in any finite system, you'll always find order. So this is a beautiful experiment from Shahal's group. I was very excited when I read about it in the archive. Direct measurement by STM, seeing Wigner crystallization. See, it puts 3 electron, 4 electron, they form this pattern. And Inwi Wu just started working with me, and I asked him to do calculations to reproduce these results. Charles' paper already had some very sophisticated calculations, but I had this thing in the back of my mind that I want to understand how the Wigner crystal evolves. So he did some direct numerical calculation. These are exact diagonalization of small 1D systems. And what we found is that indeed, when you have 4, 5, 6, 7, 8 electrons, you're going to see this sort of Wigner crystallization in 1D. And the correlation function will fall off very slowly. And I'm not going to discuss this paper in great details. We actually verified explicitly what Heinz Schultz said. And basically, we found that you have to go to very large system to destroy the correlation. It will be much easier to destroy the correlation by going to finite temperature. Here's finite temperature result, and the correlation goes away very fast with temperature. But at distance, it actually falls off very slowly.
Sankar?
Yes.
Can I ask a question? Can you go back for a second?
Yeah.
For this Schultz's paper, can you remind me, is this for 3D Coulomb or 1D Coulomb, or what
This
type?
is 1/r interaction, 3D
1/r.
Coulomb in 1D.
Okay, thank you.
3D Coulomb in 1D. That's very important, by the way. Okay, so this is the two papers in Wu who did an amazing amount of work in a very short time. One of them was directly motivated by Charles' work, directly, I give him all the credit. This is this part where we didn't really have any lattice. And what I was interested in seeing is that, is it really true that if you put electrons in a 1D confined system one by one at low density, you're going to see this charge density wave. Let's call it charge density. And the truth is, yes, you will. So these are the top line, A, is for very low lattice potential. Okay. So in a very low lattice potential, V0 is equal to 2. For low density, you do not see much charge density. So this is charge density wave. But when you go to very high density, you can call this Mott or you can call this Wigner. Okay. In the lowest one, we don't have any background lattice. We just have confinement. But the physics is very similar. This was in pure gallium. This was in a lattice. But if you look at these two figures, this and this look very similar, and this is something intermediate. Now here, what we did, we very systematically studied this transition in the collective ground state in going from a lattice to no lattice. So it's a very long paper. There are lots of results here that I cannot discuss. But what I want to tell you is that I'm showing you some selective results. Upper row is a Mott insulator. We have a lattice with 1 Rydberg depth and separation between electrons some large number. This low row, this one, there is no lattice. The lattice potential is, 10 to the power minus 3. Separation between electrons is very large. You see, the physics is very similar, except Mott is always much more localized than Wigner, which is what you would expect. But I mean, you should read the paper. We have looked at every possibility you could think of to show it's really a continuous progression in a lattice. There is no phase transition between Wigner and Mott. It's a continuous progression. You go from long-range correlation to short-range correlation as you go from Mott to Wigner. And so although we gave a phase diagram, this phase diagram is quite arbitrary. At some point, for some value of correlation, we call it Wigner. And, when the correlation was long, we called it Mott. I mean, other way around. Okay. So this is our phase diagram. So Wigner is long-range correlation. Mott is short-range, but what you want to call short and long, there is a number. That number is arbitrary. And we gave you a phase diagram. But what I want to emphasize is continuous. There is no phase transition. This is Wigner. All the over here somewhere is a gallium. And you can see that Dinwi Wu is very good. Change the lattice potential by 8 orders of magnitude. And there is no phase transition, nothing. In any one of these points, you can see identical physics if you make V0 large enough or the separation between electrons large enough. So it's all continuous physics. So whether you call it Mott and Wigner depends on the context. So now I want to come to the physics we want to discuss, Moray and Mott. So since we had set up this machinery recently, we said, well, we studied individual single period, 1 period. What if we add 2 periods? After all, this is what one is doing. One creates Moray period. We can do it in 1 dimension very easily. Just add 2 potential, and this number m gives us, this is kind of like the Moray angle. This tells you the level of incommensuration. and then let them interact. What happens? So this is, for example, the band structure. Top is the band structure. You can see for large M, this is the 1-year state. It's very strongly localized. Here is the band structure. You can see band flattens exponentially for large M, 7 and 8. Think of this large M as small angle twisted bilayer graphene, or this twisted Moore TMD system. So all that physics is here. The band flattens, and here when M is 1, this is flattening by 4 orders of magnitude. Okay. So now we turn on Coulomb interaction. Okay. T separate exponentially, we turn on Coulomb interaction. What would happen? Well, here is a result for relatively small Coulomb interaction. And what you find is that here is VC's M is equal to 1. So we don't fool around with Coulomb interaction. It's a real Coulomb interaction. But since M is 1, effective value of VC over T is small, because T is large here. So you can see that you find nice metallic band state, exactly what one should find. We are not changing anything other than M. Now we put M is equal to 7. We add a second potential with M7. Look what happens. Immediately you start seeing correlated insulator phase. This is what Pablo would call correlated insulator. It's not quite Mott, but the system is almost localized now, because all we have done is put a period. And if you put M is equal to 8, it localizes even more, because what is happening is exactly the physics that you know. VC over T is increasing simply because the band is flattening. And these are real calculations with exact diagonalization. So this is Moore-induced Wigner crystallization. What more can one say? Well, what more we can say is that the system is not really periodic. It's quasi-periodic. So somebody made this comment today that the whole sample is the device. That's a very good point. The size of the sample matters, because here we're approximating an irrational by a rational. So when you do that, basically system size will matter, because to what extent you're approximating the irrational by a rational will depend on your system size. So basically you can think of this quasi-periodic potential as a periodic potential plus a disorder. And the amount of disorder depends on the size of your sample. And when you work it out and do the calculation, you find what you'll find is that this correlated insulator is very fragile. If you didn't know anything, it would look like that it is disappearing often depending on system size. Actually, it's not disappearing. You are hitting different rational approximations to the irrational. And so the conclusion is that if you do an experiment, you will conclude that correlated insulator is very fragile. It's fragile because of this rational approximation irrational. Again, I'm not going to discuss this in great details. I really want to talk about 2D systems, but you should read this paper where you work it out completely and show you how this fragility affects results, and this various Wigner or Mott gap or correlated insulator gap, how that stays or goes away depending on what level of approximation you are using.
Okay, Sankar, I think that we should start to, 5 minutes or something like that. Okay.
Yep. I would be done in maybe a little bit more than 5 minutes, but I'm coming to the end. Okay. So now, and I suspected by the time I come here, I'll be running out of time. So this is now talking about things that we heard about in this talk. So quantum phase diagram of a Moore-Hubbard model. Okay. So you have a twisted transition metal dichalcogenide. So this is the system. We have seen it already. So I'm summarizing all the results in this slide since I know I'll run out of time. Okay. So we first did the band structure correctly, full band structure calculation. Then we mapped it on a effective Hubbard model to get the Hubbard parameters. But this is what is called an extended Hubbard model. This is not your just on-site repulsion. We include all the next nearest neighbor repulsion according to Coulomb interaction. Okay. And then we have just 2 parameters in the problem. One is effective dielectric constant that tunes the Coulomb interaction and the angle, which determines your band structure, and then of course filling. So this is for filling, this is for theta is equal to 3 and a value of epsilon 10. We calculate the gaps at various fractional filling. Okay, this is the band gap 1, and there are various fractions. Today we heard from Feng Wang, gaps at 1/3 and 2/3. Those are indeed the largest gaps in our calculation, but there should be gaps at other filling also. Now, this is not, of course, an exact diagonal calculation. This is a 2D calculation. This is a very large mean field calculation, keeping like something like 15,000 next nearest neighbor term. So this is, for example, the phase diagram in epsilon theta space. This is for, I believe, filling half. I'm not sure what filling, for some specific filling. But what we find that name your favorite phase, and it probably exists somewhere in this system. I was actually totally amazed how rich this system is. I did not even want to work on this field because I said, oh, there'll be nothing new. It'll be again Wigner crystal in another place. But that's not true at all. So we found antiferromagnet, a tetrahedron phase, a normal metallic phase, various Kagome symmetry breaking topological phase, ferromagnetic phase, Kagome time reversal invariance breaking phase, and ferromagnetic block metallic phase. All of them in this system for some angle, okay? So many known and many unknown quantum phases are lurking here, okay? And some of them
Can I ask a question here?
Do you want to wait just a few minutes? Let me finish.
Okay, fine, yeah.
That may be better, okay? So what do you do? I want to just quickly emphasize the difference between graphene and, you know what? I'm going to pass this one. If somebody asks, so this is the band structure calculation. It's in our papers, but we do what everybody else does, and then in the end, you have three parameters: this V, psi, and W. Then you fit them, and we fit them by using the STM data that was talked about here. We fit our band structure parameters, so they're reasonably reliable, I guess. And then we do our fitting to the generalized Hubbard model. Okay, so now we have a generalized Hubbard model, and then we do a full mean field theory. Now, how do we start the mean field theory? Let me just go there. Let me skip this part since time is running out. So let's do the classical calculation first. So let's put the kinetic energy to be 0. So then we can do the classical calculation exactly. And for each filling, then we know the exact classical phase. So we start our mean field calculation with this ansatz, okay? And we take all the next nearest neighbor. Heining Pan tells me that we kept 15,000 next nearest neighbor terms to have convergence. And then you do the calculation. And this is, for example, a direct comparison with work that was presented, I guess, yesterday. So you can see that the gaps are, pretty comparable at various filling. So maybe we are understanding something. This cannot be a coincidence because we did not, other than this epsilon, we did not really fine tune anything. So this phase diagram is for half. This is phase diagram for 2/3, 1/3. This is phase diagram for 1/4, 3/4. And I think that I should stop here. I should stop here, basically showing you the papers, okay? All these 5 papers are on the web, and the color scheme are who did what. And thank you for your patience.
Thank you for the exciting talk. Okay, questions? I know that there will be a discussion session, but probably people will want to have a short break.
I'm happy to answer questions. I may not be able to answer questions, but I will try.
So, any questions? Or do you guys want to move? Okay, Eugene, you can actually ask.
Actually, I guess you partially answered it. So when you do your mean field calculations, are you sure that you sort of cover all possible types of symmetry breaking?
Yep.
Because there may be something, I don't know.
Okay,
because if you just,
it's too dangerous a thing to talk about, but exactly. We found many phases that no one has talked about. So we look into many possible phases, some of which we did not find a stable ground set. For example, a Haldane phase, we tried very hard to stabilize it, and mostly it's not stable, for example. It's discussed in our paper. But we do try, all the phases we could think of, and some that nobody has thought of before.
Okay, but I guess, to be more specific, do you already assume a certain period? Because what you can also do is unconstrained Hartree-Fock.
This is a restricted Hartree-Fock. Because unrestricted Hartree-Fock, we simply don't have a large computer enough time to do it. But you make a good point. Perhaps that should be done.
Okay, Philip Kim.
Shankar, I think you skip it over, but can you just go back to the slide about the comparison with the graphene and the TMDC?
Oh, yeah, sure. Yeah, I skipped over because, it's running out of time. So let me, yeah, here. So the differences are that, this is the standard group symmetry difference. But the biggest difference, I think, is the fact that there's a big gap here. Okay. And then the magic angle. Okay. So, so it's an energetic question now. Here the spin orbit coupling is very, very strong. In graphene, it's very, very weak. So this very strong spin orbit coupling, I think, does not allow the quantum ferromagnet phase to be stable here. Okay. Whereas this is stable here. The other band is very far away. In graphene, the other band is very close by. But these are the theoretical differences which come into doing the calculations.
Okay, the next question will be about Leo.
Oh yeah, I just had a simple question. Shankar, can you remind me, what is the current status of Wigner crystal based on just sort of first principles numerics?
Yeah, first principles numeric. Yesterday, David separately talked about it a little bit. Apparently, the state of the art is still this 2006 or 2007 paper from Cambridge, I think. And in 2D, the claim is the Wigner crystallization at zero temperature, quantum Wigner crystal at zero temperature happens around RS40, and the spin structure of the ground states is still an open question. Ferromagnet and antiferromagnet energies are very close by, and Thouless's original argument that depending on the crystalline structure, whether it's square or triangular, should prefer ferromagnet, antiferromagnet is not quite correct. You have to take larger and larger spin ring exchange. So my understanding from what David said, and this is, by the way, my own conclusion also, we could not even settle this in the 1D calculation because the exchange energy is so tiny, Leo, that I was not comfortable. Of course, in 1D, there are other issues. You can do the calculation exactly in the infinite system. It's a spin liquid type ground state. But let's say that that's not what you're interested in. You just want a finite system and count the number of spin. It's very difficult. You're dealing with comparing numbers like 10 to the power minus 20 times something.
Okay, and this is, you quoting this is for continuum in 2D?
This is what I'm quoting is J-Liam continuum 2D fixed node Monte Carlo, where they vary the node. Yeah.
Thank you.
Any other questions? If not, then I suggested we take a 10-minute break before we actually start next discussion session. And the next discussion session, I believe, will be chaired by Eugene. Eugene, is that the plan?
I have to admit, I didn't think of this,
Okay.
but yeah, okay, yes, let's, the two of us will take the lead, yeah.
Okay. So I will have to leave at around, say,
Sure,
6
yeah.
Okay. So anyway, so let's take a 10-minute break and thank everyone for the wonderful talks. And then as a member of the organizing committee, I would like to thank everyone who participated. Thank you so very much. It was a really stimulating mini symposium. Thanks, Sankar.